Hello. Okay, so let's then start. So in the last class we discussed about the Gauss elimination method, and today we are going to generalize this method. Now suppose there are n number of linear equations. This n may be any number, suppose 10 or 11 or anything, and here there will be now n number of variables from x1 to xn, and there will be also this n number of non-homogeneous part, this b1, b2 up to bn, and there will be these coefficients a11, a12 up to ann, and we need to solve this n number of linear equations. And the approach will be same. There will be two steps. The first step will be forward elimination, and the second step will be back substitution, right? So in the forward elimination we will carry out several loops, and in each loop we will eliminate a variable. In the first loop we will eliminate these x1 values, in the second loop we will eliminate x2 values, in the third loop we will eliminate x3 values, like so on, right? To make the coefficient matrix having an upper triangular form, right? So let's start from dividing the coefficient of x1 in this equation. In the first equation, start by dividing the coefficient of x1, and the form will be like this. The coefficient of x1 is a11, divide it everywhere, and then multiply the coefficient of x1 from equation 2. Multiply the coefficient of x1 means a21 here in the equation 1, and then subtract this equation 4 or this modified equation 1 from equation 2, right? And what will be the result? The result will be that this term will be eliminated, right? So here you can see that if you carry out that process, then you will see that this a11 or the term was a21 x1 will be eliminated, and all these other terms so here you see that all the other terms are there, but this a21 x1, that term will be eliminated from the second equation here. So, and if you repeat this process to eliminate all the x1 from all other equations, so after this first loop of forward elimination, the system of equations will become like this, right? All these x1 values will be eliminated below this first equation, and all the other values will remain there, right? So how to carry out this whole process? First you have to start with this equation. This is your central equation, and here you need to divide this coefficient of this x1 everywhere, and multiply the coefficient of x1 from these equations here, and subtract that modified equation from all other equations, right? And in that way you will eliminate all these x1 values, and after the first loop of forward elimination, these x1 values will be eliminated. Then what will happen after the second loop? After the second loop, all these x2 values will be eliminated, right? So for the second loop, the term associated with x2 from equation 7 to equation n dash are eliminated, and start with the same procedure, divide by a22 dash. So here this equation will be your central equation. So first what you have to do, you have to divide this whole equation by the coefficient of x2, right? And then multiply the coefficients of this equation with this equation, and then subtract it from all these equations. By the result, you will get that all these x2 values will be eliminated. This is not from equation 7, this is from equation 8, right? So up to from equation 8 to equation n, all these x2 values will be eliminated. Here you can see that. So after this second loop, you see that all the x2 values from equation 8, they will be eliminated. And now this will be the modified set of equations. Similarly, after this n minus 1 number of loops, what will happen? Here these x2 values will be eliminated, then x3 values will be eliminated, then x4 values will be eliminated, and finally xn minus 1 values will also be eliminated. Then in the last equation, just xn value will remain, right? So all these values will be eliminated, and the coefficient matrix will have an upper triangular form, right? And here in these equations, the prime symbols and the values in the superscripts represent the number of computational loops needed for forward elimination method. Here you see that this one dash represents these coefficients or these constants are found after the just one loop, and these are found after second loop with 2 dash. And similarly, if there is a superscript like n minus 1, then these constants are found after n minus 1 number of loops, like so. That is how you carry out the forward elimination. After n minus 1 number of loops, you will get the upper triangular form of the coefficient matrix. Then what is back substitution? Back substitution is the method when you find all the variables, the value of all the variables. Here first you need to find what is the value of xn, and the xn value will be nothing but just this constant here divided by this constant, right? Like why the screen is freezing down? Yeah. Now this xn value will be just this bn here divided by ann, right? So start from this last equation, and the value of xn will be like this, and from this value of xn you have to find then the value of x minus 1, then xn minus 2 up to x1, right? So you have to go in the reverse order, and you have to find all these variable values. The unknowns xn minus 1, xn minus 2, x2 up to x1 can be obtained by using back substitution, and the general formula is this. How to get this general formula? You see that if you want to find this x2 value, what will be this x2 value? This x2 value will be b2 dash minus addition of a23 dash plus x3 up to a2n dash xn divided by a22 dash, right? So similarly, you can see here that this xi value is bi minus summation over j equals to I plus 1 to n aij xj divided by aii. This aii is the coefficient of xi and bi is the this term here, that is x2 equals to b2 and divided by this coefficient of x2, and here you can see that the summation is going from this j value is 2 plus 1 to n, right? So here you can see that the summation is going from 3 to n. So here you see that the summation over j, the second index, is going from I plus 1 to n. So it will, for this case, it is going from 3 to n, and here for the general case it will go from I plus 1 to n, right? And that will be the general result. Is it okay? Yeah. Now we will see how to implement this in Python. Then there is also Gauss Jordan method, and that is just an extended version of this Gauss elimination method, and in that method you have to carry out this complete diagonalization. There is no upper triangular or any kind of form. You have to diagonalize this matrix, and there will be only the diagonal elements, and then you can easily find what will be the values of x1, x2 and x3. You can read yourself, and that is available in that book on page 73, and it is not much important. And these are some problems you may want to do or not, it depends on you. And here there is a problem to solve this circuit, and the problem is to first you have to apply Kirchhoff's law and just write the system of equations you get and solve them using the Gauss elimination method or Cramer's method. You can choose anyone. You have to solve for the currents, right? This I1 and there is I2 and I3. So there are three variables you have to solve here. Okay, so let's implement this generalized version of Gauss elimination method now in Python. Let's see how to do it using a computer. So let me just stop presenting here, and now is it visible? Okay. Okay, so let's start. And the first step is to import numpy. Here we are importing numpy as np. Then input the number of unknowns you have. Suppose you have 3 or 4. In the previous example we had 3 unknowns, x1, x2 and x3 in the last class. And then what is this? This A is the coefficient matrix, right? If there are 3 unknowns, then the coefficient matrix will be a matrix of order 3 cross 3, right? So here we are initializing a matrix, a coefficient matrix having all the index as 0. np dot zeros, n comma n means here it will give you, if n is 3, it will give you a 3 cross 3 matrix with all the elements as 0. Then initialize the variable matrix, a column vector of suppose 3 elements, and then this B, the non-homogeneous part, or in the right hand side also there will be suppose 3 elements, suppose B1, B2 and B3, and they are all 0 now. All the elements, all these matrix are 0 now, right? So np dot zeros. Now let's define the matrices. What are the elements? Just initialize them first, and then we will modify those elements. Although in the place of 0, we will put some value, right? So for I in range n and for j in range n, we will find or now we will modify the aij values, right? Means what are the elements in the matrix, and then again we will also input all the bi values or the non-homogeneous part of the equation. So here we will input all the coefficients from the coefficient matrix, and then we will here input all the non-homogeneous part. So let's do that first. So here I am inputting the number of elements or the number of unknowns as 3, x1, x2, x3 or here. Then let's input all the elements of coefficient matrix, and here I am inputting all the coefficients from the last problem we did in the previous class, right? So if you have your note, you can see that what are those elements. The first element is 4, right? And then the second element is -4. Then the third element is 0. Then the fourth one is -1. Then 4. Then -2. Then 0. Then -2 and then 4. And now the non-homogeneous part, what is B0? B0 is 4. Then B1 is also 4 and B2 is also 4. So now you have given input for all the quantities, like all the coefficients of coefficient matrix A00, A01 and all that, and also the non-homogeneous part. So here you notice that we are starting with 0, not 1, right? So when we are doing the problem, the coefficients were like the first coefficient was A11, not A00. But here you see that the coefficients are starting with A00 values, because in Python the indexing starts with 0, not 1. So that is why you see that the first coefficient is A00, then A01, A02, and similarly instead of B1, B2 and B3, we are writing B0, B1 and B2, right? So that is the problem here. That is, sometimes it is confusing because in your note the indexing starts with 1, and here in Python the indexing starts with 0, right? Is it okay? Are you getting my point? Yeah, you can start, but that will be a bit complicated because naturally when you write this age range is n, then it will start from 0, and if you want to start the indexing from 1, then what you will write? The I in range 1 to n, right? That you can do, but I mean, people don't do it. They keep it as it is, and in your note you may change it from 0, right? So if you do this all the time, everywhere, that will make it more complicated in the code. So that is why we don't do it. And in your note you can change the indexing and start with 0 instead. That will be not much problem. You will get used to it. right? Is it okay? Okay. So here I have given the input for A and B matrix, right? So this A and B matrix are inputted here. Now let's make the upper triangular form. Now this is the forward elimination part. This code block here is executing the forward elimination, and this second code block here is executing the back substitution. So now this part is a bit complicated. So here first see that we are starting with for k in range n, then for I in range k plus 1 to n. So here you can see that here the comment is that it is the pivot row. So this you have to start with in the forward elimination. You have to start with the first row, right? Then for I am explaining it for I in range k plus 1 to n. This bi value is equal to bi minus bk into aik divided by akk. Then in this line, first we are updating the right hand side or the non-homogeneous part, right? So here you see for k, suppose n is 3, we have 3 unknown variables, suppose x0, x1 and x2, right? So here you see that for k in range n, for I in range k plus 1 to n, this bi value will be like this, and here in what will be the values in the first iteration. For this for loop, in the first iteration, the value of k will be 0, right? For k in range n, that means for k in the range 3, then k value will vary from 0 to 2. So in the first iteration, the value of k will be 0. Then it will go to the second line of the loop. For I in range k plus 1 to n, k is 0. Here k is 0 in the first line. Then I will be here 1, right? Because it will start from 0 plus 1, and that is I is 1, right? So I will go from, if k is 0, then I will go from 1 to n, and that is 1 to 2, right? So then it will what will be its value? So we are writing bi, that means bi is b1, and b1 equals to b1 minus b0, and divide this by a00 and multiply this. So that is what we did in the forward elimination in the last class, right? So first you have to divide the first equation with this coefficient of x1 and multiply it with the coefficient of x1 from the equation 2, right? And that is how you get the modified value of b1. Are you getting my point? What is happening here? Yes. So here you can see that, these are the equations. So it will be easier if I had the equation. So do you have the equations in your note or anything from the last class? Can you open it? We did an example from the last class. Yes, that equation. So how do we did in the forward elimination in the first loop? In the equation 17 in my note. Yes, and then multiply it. Yes, So here you see that. So here the what was on the right hand side in the equation number 14, it was 4, right? Then what we did? We did first we divided it by the a00, right? 4. What is a00? A00 is the coefficient of x1, that is 4. Then what is a10? A10 is the coefficient of x1 in the equation 15, right? So that is how you get the modified b1, this b1 dash, and what was b1 dash? That was 5, right? Are you getting my point? So b1 is 5 and b0 is 4, right? So here in the equation, in the equation 22, you see that the b1 is 5, and that is how you get the b1 and b2, the modified b1 and b2 values. So first we are updating the right hand side, and then you have to update the coefficients itself. Now see in my screen now. So here you get the modified b1 and b2 values if you carry out this loop, and then for j in range k plus 1 to n, then you have to carry out this thing here, that for j in range aij is equals to aij minus aik into akj divided by akk. So here how we are updating the coefficients also in the same fashion, and while doing that, we will now start from this a11 value. That is quite weird, because when you want to update the coefficients, you need to start from this quantity here, right? A10, right? First you have to make this one 0, right? Are you getting my point? But we are starting from here, not here. We are starting from this a11, right? So this is the 0th row and this is the 0th column, and this one is the first row and this is the first column, right? So this notation is a bit weird, but you have to hold into it. So this is the 0th row, remember it, this is the 0th row and this is the 0th column, and this is the first row, this -1 4 -2, and this is the first column, and then this is the second column, and this is the second row here, right? So we are now for j in range k plus 1 to n. So here I was 1, here in this loop I was 1, and here j in range k plus 1 to n. So in the beginning of loop k was 0, and now it will be aij, that means a11 will be a11 minus divided by this a00 and multiply it with the a01 value here, and you will get the modified value of this a11. Are you getting my point? What is happening here? So the same process we did for this b values, we are doing again for a11, and here we are not starting with this quantity, we are starting with this one, because ultimately we will not need these quantities. Why? So what about these values? So here is something very interesting. When we are executing this program, you see that with these values, this -1 0 -2, if you don't even change them, ignore them, they are 0 anything, it doesn't matter. If you just modify these elements of the upper triangular form, that will be it. Because when you will be doing the back substitution, you see that these quantities will be not needed, because our method is like that, right? So why? Because if you see that in the general form of the back substitution, you see that xi is bi minus summation over aij xj, and the summation of j is from I plus 1 to n. So here you just need these quantities for back substitution. This 4 minus 2 4, these quantities you need. These quantities, it is the whatever their value, these values doesn't matter. You just need these values in the upper triangular form for the back substitution. So here something that is something weird, that if you are performing this forward elimination, this may if there is an viva, then they may ask you about it. So if you are doing this in a program, so a lot of time you will see that they are ignoring these values. We are not updating here in the beginning. We are not updating this A10 value. This is the A10 element, right? We are not updating it. When you see that, when we are starting the loop, we are not first updating A10. We are updating A11. Then we will update this one, and in the next loop we will update this one. We will ignore all these things, and that will do. That will be not a problem. Are you getting my point? Yeah. So that is how it works. So here this A11 will be A11 minus this quantity here for the first iteration. In the first iteration of this entire code of block, right? A block of code, thus that will be the result, right? So this is how you get the upper triangular form. And if you want to set them 0, if you don't, just ignore them, the terms in the below the diagonal, if you just ignore them, that will be also fine. But if you want to make them 0, you can explicitly make them 0 here. Here I am making this aik is equals to 0. And now if I just change them or just make it a comment, then that will be also fine, right? If you can make it as a comment, then if you run this simulation or run this code, then you will see that the result will be same. The result will not change. So here for showing you, I am keeping it as it is, and here if I just run this print a now, the print a is already there. So here you can see that this is the coefficient matrix now in the upper triangular form. All the elements here are non-zero, but here the elements in the lower triangle, they are 0. Now you have to carry out the back substitution. This is easy. We'll just start with this xi equal to bi and just implement the equation 17. Here if I can show you, here is equation 17. Yes, so here in the back substitution, just implement this equation. Start with xi equals to bi, then calculate this term here. You have all the coefficients, all the aij coefficients. Just write in this form in Python, and here we have done that. Here first you have to take the sum value, this sum value as 0, the summation value. You have to take some value of the of this term is 0 first, and then update the sum value, that is sum equals to aij xj, and the j is in the range 1 plus I to n. So first you have to calculate this summation here aij xj, and then subtract it from bi, right? Subtract it from bi, and the initially this xi was bi, so xi will be xi minus sum, and then finally just divide it by the coefficient of xi. And what was the coefficient of xi? Coefficient of xi was aii, right? Then here we are also dividing it by aii and subtract the sum here, and then you will get the, now if I run it, right, the solution is x0 means x1 is 4.5 and x1, that means x2 in your note, that is 3.5, and x2 here, that is in your note x3 is 2.75, right? Is it okay? So that is how you carry out the Gauss elimination method. So if you go through it, and you may try this thing here, and you may also solve for other set of equations for variable n may be 4 or 5, or you may do the problem that is given in the example, in the exercise, that is that circuit to solve for the currents. Okay, so that is it for today, and in the next class we will talk about curve fitting. Okay, so let's meet tomorrow same time, right? This 8 a.m. right? Okay then, so goodbye, bye bye.